A sickening groan echoes through the submarine as it descends into the darkness of the ocean. As the vessel goes deeper and deeper, the pressure pushing against its hull becomes greater and greater. At some point, the pressure is too much. The steel and titanium hull collapses, and the entire submarine folds in on itself, consuming anything and anyone inside. There are some inherent risks with diving deep into the murky depths of the ocean in a submarine. You could run out of air, end up poisoned, or be crushed to death. If you find yourself in a sinking submarine moments before it implodes, you're in for a pretty horrible death. The good news is that it'll be over in a matter of milliseconds. The bad news is your body will be nothing but a sack of crushed bones and muscles as it sinks to the bottom of the ocean floor. A sudden pressure change of about 50 psi, or 3 to 4 times Earth's atmospheric pressure, is enough to cause your body some serious harm. This amount of pressure occurs in around 112 feet or 34 meters underwater. For a submarine, it's not very deep, but as you descend deeper into the ocean, the pressure continues to increase to the point where your ribs would crack, your lungs would rupture, and you would die before you even had the chance to drown. To be clear, your body would only be crushed by a sudden change over 50 psi. If you experienced a gradual change in pressure, your body could withstand around 400 psi, or 27 times Earth's atmospheric pressure. In fact, the record for the world's deepest scuba dive is 1,090 feet, or 332 meters. Unfortunately, the pressure change is not a gradual one when a submarine implodes. Before we get into the gruesome details of death by submarine implosion, we need to understand what an implosion actually is, how a submarine keeps it from happening, and what can cause the catastrophic event. An implosion is the exact opposite of an explosion. When something explodes, a large amount of energy is released and moves in an outward direction from where the initial reaction occurred. An implosion, on the other hand, is when a large amount of force moves inward. For example, when air or water pressure is greater outside of a container than inside, such as in the submarine, the difference in pressure results in an inward force all around the container. This is because pressure and forces in the physical world want to be in equilibrium. In order for this to happen, the pressure inside and outside of the submarine needs to be the same. Hence why the much higher water pressure outside of the sub pushes inward, as the water naturally wants to fill the much lower air pressure within the submersible. Just to give you a better idea of how much pressure there is deep in the ocean, let's run through some scenarios. Right now, if you're watching this video at sea level, there is 14.7 pounds per square inch of air pressure pushing against you on all sides. This is also known as 1 atmospheric unit, or ATM. If you're high up in the mountains, the air pressure is slightly less, as there's less atmosphere pushing down on you. If you are in a deep hole, the pressure pushing down on you would be slightly higher than the 14.7 psi, as there's more atmosphere above you than at sea level. Since our bodies and every living thing that lives on land evolved to withstand that amount of pressure, it's not a big deal. This is because the fluids in your body are pushing outward with the same amount of force as the atmospheric pressure is pushing inward. However, as you descend deeper underwater, this pressure increases. This is because you now have the combined weight of the atmosphere and all the water above you pushing down on your body. With each foot or meter you descend underwater, that much more weight pushes down on you. So, what exactly does this mean? If you're under a few feet of water, your body won't register much of a pressure change. This is because there's just not that much additional weight pushing down on you. However, if you descend to a depth of around 33 feet, around 10.06 meters, the amount of water pushing on you is comparable to the pressure the atmosphere exerts on your body. This means that you would now have approximately 29.4 psi of pressure pushing inward on your body, or 2 ATM. This pattern continues every 33 feet or 10 meters as you go. At 100 feet or 30.5 meters, you have just over 3 ATM or 44 psi of pressure pushing against your body. This would be like having 4 1-gallon sized tins of paint pushing on every square inch of your body. The fluids inside of you would still be able to push outward with the same amount of force, but as you descend even further, the pressure will eventually become too great and your bones will begin to break. An Ohio-class nuclear submarine has an operational depth of 984 feet or around 300 meters. However, these vessels can reach 1,640 feet or 500 meters if circumstances call for it. Now let's assume you're on an Ohio-class sub at operational depth. The pressure pushing against the hull at 984 feet is 410 psi, or 30 times the pressure of the atmosphere pushing against you at sea level. If the hull gave under this pressure, 410 pounds or 186 kilograms of water would push inward on every inch of the sub's hull until it imploded. and the 1 atm on the inside of the vessel equalized with the 30 atm on the outside of the vessel. This would happen instantaneously and would crush pretty much anything inside the sub except for dense metals. However, for the adventurous, there are subs that can descend much deeper than the 300 meters below sea level. Recently, the Titan submersible was lost while heading to view the Titanic wreckage at the bottom of the Atlantic Ocean. Several submersibles have made this journey. The first crewed expedition was conducted in 1986 aboard the DSV Alvin. Alvin descended to a depth of approximately 12,500 feet or 3,810 meters. This means that the pressure pushing inward on the vessel was about 5,600 psi or 381 atm. A sudden catastrophic failure resulting in an implosion at this depth would leave very little but mangled pieces of the hull behind. This is what happened to Titan, which we'll look at later on. Interestingly, there are animals that have no problem surviving the crushing pressures deep in the ocean. For example, most whales can dive to extraordinary depths where the pressure would pulverize a human, and even some submersibles. Sperm whales descend over 7,000 feet or 2,134 meters below the ocean surface to hunt for giant squid. This means that their bodies experience over 3,100 psi of pressure, or approximately 213 atm, before surfacing for another breath of air. Whales are able to dive to extreme depths thanks to the flexibility of their bodies. Their ribs are surrounded by loose, flexible cartilage that allows the skeleton to safely collapse and expand as needed. This prevents the whale's bones from snapping. Human skeletons, on the other hand, cannot withstand anywhere near the amount of pressure a whale can. This is one of the reasons why we're limited to diving just a few hundred feet under the water. When the hull of a submarine fails, all of the water pressure that is pushing inward instantaneously equalizes as water fills the space where the hull once had been, destroying anything that can't withstand the massive and instantaneous pressure change, such as a human body. But what does this look like, and how painful would it be to be crushed in a submarine implosion? Before we answer these questions, let's figure out how a submarine works and how it's able to withstand the massive pressure of the depths of the ocean. On a basic level, all submarines use air and water to control their buoyancy and allow the vessel to rise or sink in the water. When a submersible needs to rise to the surface, the sub's ballast tanks fill with air, reducing the vessel's density and making it more buoyant. This allows the submarine to overcome the force of gravity pulling the ship downward. In order to dive deeper, these ballast tanks are purged of air and filled with water. This causes the submarine to become denser and less buoyant, resulting in it sinking. If a submersible's crew wants to remain at a certain depth, the ballast tanks need to be filled with the right proportions of water and air to make the vessel neutrally buoyant. This prevents the sub from rising or sinking. Implosions of submarines have occurred in the past when vessels were damaged and couldn't feed air into the ballast tanks. This resulted in the submarines descending deeper and deeper. Every vessel has its breaking point where the water pressure becomes too great, and the frame starts to bend or collapse. When this happens, the submarine implodes. But there are other major concerns aboard a submarine other than just catastrophic failures. The only reason that a submarine implodes is that the pressure on the inside of the vessel is significantly lower than the pressure on the outside. However, this is also what allows the crew of a submarine to survive while inside the hull. If the inside pressure is equalized with the pressure outside of the submarine as it descended, an implosion wouldn't be possible because there would be no sudden change in pressure. Hence why ships resting deep on the ocean floor aren't just crumpled balls of metal, but still maintain their shape and structure. As a sinking ship descends downward, water floods every compartment, equalizing the pressure inside and outside of the ship. Unfortunately, that kinda defeats the purpose of a submarine. A much lower pressure must be maintained inside the submersible than outside so the crew can breathe and aren't crushed to death. The air we breathe isn't just oxygen, which means that the air inside a submarine is a mix of several gases. An average breath is made up of about 78% nitrogen, 21% oxygen, 0.94% argon, and 0.04% carbon dioxide. This is more or less the composition of the air aboard a submarine. When we exhale, the air released from our lungs contains around 4.5% carbon dioxide, which is a byproduct of the processes that keep us alive, such as cellular respiration. What all this means is that submarines have complex systems to allow the occupants on board to breathe and not be crushed. This also means that an implosion is not the only thing you have to worry about if you're deep underwater in a submersible. Oxygen needs to be constantly replenished so you don't suffocate, and carbon dioxide must be removed so you aren't poisoned. In smaller vessels, the air mixture might be self-contained with a limited supply. Once the supply runs out, that's it. The crew either needs to surface or they'll die. On larger vessels, processes such as electrolysis can be used to separate water molecules into their independent parts of oxygen and hydrogen. The oxygen generated this way can then be circulated through the vessel for the crew to breathe. This means that these types of vessels can stay underwater indefinitely. The only limitation is the amount of food it can hold to feed the crew. To remove carbon dioxide from the air, soda lime, which is made up of sodium hydroxide and calcium hydroxide, is used inside scrubbers. The soda lime traps carbon dioxide and removes it from the air. Problems arise when these systems fail, and the air inside of the sub becomes a mixture of gases that is not safe to breathe. For example, if the carbon dioxide or carbon monoxide levels become too high due to a malfunction in the scrubbers, the entire crew could pass out and eventually die. At that point, the submarine would be left to its own devices, which could ultimately lead to it sinking and imploding. Another threat to submarine crews that could also lead to a catastrophic failure and an implosion is the cold temperatures of the ocean. The surface will almost always be warmer than deep water. Submarines typically travel through waters that are around 39 degrees Fahrenheit or 4 degrees Celsius. The heat from within the submarine is lost through the hull into the frigid dark waters around it. This means that electric heaters need to be constantly running to keep the crew alive. However, these cold temperatures can also lead to deadly problems and result in a series of events that lead to an implosion. We'll look at how this happened to at least one submarine later on. The complex systems within a submarine mean that any number of things could go wrong. There are many ways to die deep under the waters of the ocean. Suffocation is one. Freezing to death is another. Both of these would be terrible ways to go. They would take time to kill you while you looked into the blackness of the sea praying for someone to rescue you. An implosion, on the other hand, would occur in milliseconds. You would be crushed to death long before your brain could even register something was wrong. So although death by submarine implosion would be a horrible way to go, it would be somewhat merciful as there would be no suffering. One moment you'd be alive and the next there would be practically nothing left of you. Now let's go examine some of the submarines that have imploded in the past and what happened to their crews. There were no survivors in each one of these tragic events. The reason for this is that if a submarine implodes, there's zero chance anyone could survive. Their bodies would have been instantly annihilated by the pressure change, and anything that did remain would sink to the bottom of the ocean. In 1963, the nuclear-powered Permit-class submarine USS Thresher and its crew suffered a gruesome fate in the depths of the Atlantic Ocean. On April 9th, the Thresher began dive trials off the coast of Cape Cod after it had been refurbished and outfitted with new components. At 7:47 a.m., the submarine descended to a test depth of 1,300 feet or 400 meters. The crew began to inspect the ship for leaks or any other malfunctions and found none. Later in the dive, one of the pipe joints on the ship ruptured either due to pressure or faulty installment. This leak occurred in the engine room, and soon after it started, the compartment began to fill with mist. The captain was informed of the leak and would have made the decision to blow the ballasts and rise to the surface. The pressurized air in the pipes instantly began to cool and condense, leading to moisture freezing in the pipes and stopping the flow of air to the ballasts. The water leaking from the faulty pipes likely came into contact with wiring and electronics that then caused them to short circuit, leading to an automatic shutdown of the submarine's reactor. As a result, the submarine lost propulsion and could neither steer toward the surface nor fill its ballast tanks with the air necessary to increase buoyancy. The commander likely ordered propulsion to be shifted to the emergency battery-powered backup system. The crew rushed to get the leak contained and then would have begun to restart the reactor to get the main power back online. This process would have taken at least 7 minutes once it was initiated. At around 9:13 a.m., the commander of the vessel used the underwater telephone to transmit a message to a naval craft on the surface that was there to assist if anything went wrong during the trials. The message was garbled, but the words "experiencing minor difficulty, have positive up angle attempting to blow" could be made out. Due to flooding in the engine room, the USS Thresher was becoming heavier. This caused it to descend deeper. A second attempt to purge ballasts of water was performed, but the ice in the pipes blocked the pressurized air from reaching the tanks. At 9:17 a.m., a second transmission was sent. Decipherable words in this message were "exceeding tested depth." This meant the Thresher had passed 1,300 feet or 400 meters below sea level. The pressure at that point would have been over 588 psi or 40 atm. 1 minute later, the naval ship on the surface detected a high-energy, low-frequency noise. This was the sound of the USS Thresher imploding, killing all 129 crew members on board instantly. The submarine most likely suffered a catastrophic failure due to the high pressure at a depth of around 2,400 feet or 730 meters, which was around 400 feet or 120 meters below the vessel's maximum depth. The pressure pushing inward on the submarine was 1,073 psi, which was 73 times greater than the pressure on the inside of the vessel. Everyone inside the sub died within a tenth of a second after the submarine imploded. Another sub that imploded was the Argentine naval vessel Ara San Juan. This submersible was a TR-1700 class diesel-electric submarine. On November 16, 2017, the submarine and its 44 crew members went missing in the San Jorge Gulf. Argentina, Brazil, Chile, Uruguay, Russia, the United Kingdom, and the United States all sent vessels to aid in the hunt for the missing submarine. After 2 weeks of searching, no sign of the San Juan or its crew had been found. The search turned from a rescue mission into a salvage operation. The following year, the San Juan was located by a remote submersible at a depth of 2,976 feet or 907 meters. The wreckage of the submarine covered an area of 230 feet or 70 meters. When the submarine imploded, its hull was torn apart. All 44 members of the crew died instantly as 1,338 psi or 91 atm of pressure crushed their vessel. This brings us to the modern day and the Titan tragedy, where 5 people lost their lives when the submersible imploded on its way to view the Titanic. Many experts theorize the catastrophic failure that caused the Titan to implode was the result of an experimental hull made up mostly of carbon fibers. Traditional submarine hulls are constructed using steel, titanium, and aluminum, all of which have been extensively tested and researched at extreme depths. This has allowed engineers to understand how the materials will react under extreme pressure. The same cannot be said about the Titan's hull. The materials of the Titan sub likely had a flaw that caused the hull to crack or collapse, resulting in an implosion. The submersible had already completed several deep dives, which may have caused the weakening of the hull, resulting in a catastrophic failure and implosion of the vessel. Like all submarine implosions, the Titan catastrophe was instantaneous. All 5 people on board were instantly crushed, and the remains of the submarine sank to the bottom of the ocean. Its pieces came to rest approximately 1,600 feet or 488 meters from the Titanic. All human constructs are bound to have flaws. Submarines are no different. Suffocating to death or drowning would be a terrible way to go. However, there is something truly terrifying about being alive 1 second and having every bone in your body crushed to dust in milliseconds. This would be a painless death, but it would leave very little for your loved ones to mourn over after you were gone. Now watch, scientists agree this is the worst way to die, or check out most painful ways to die.